definitely an honor to be the first speaker in what's going to be a really fun week. Okay, so I'm going to be talking about reinforcement learning today. Cam just said that that's the area that I work in. I want to start off by saying that, of course, Amii works on lots of really interesting topics: NLP, AI for health, game theory. So I'm just going to give you a look at some of the reinforcement learning work that's happening within Amii. And I'm going to try to give you an overview of why I think RL is such an exciting topic, some of the things that the broader group of us in Amii are actually working on, and then a little bit more specifically about some of the things that I'm looking at. All right, so starting my slides. All right, so I want to start a little higher level. I want us to think a little bit about, what do you think about when you think about AI? Probably one of the things you do is you think about some of the smart systems you currently use. You use your Google Home, maybe you have a smart vacuum, maybe you're really excited about self-driving cars. You might also think a little bit about some of the things that are shown in science fiction. We have some of these cool droids, maybe you think a little bit about WALL-E. These are more individual robots when we think about AI in this way. I like to think of AI in a slightly different way. So when I think of AI, I think of supportive AI. I see AI working with us to make us more effective. So let me give you two little examples here. So one example here is a robot trying to help a doctor prescribe better treatments. So you could imagine that the agent can take a lot more information than we can. They can look at patient history, they can look at lots of different blood work information, they can look at genetic information. They can take this high dimensional input and actually propose many different treatment options. And now the doctor can do what they do best. They can look at higher level information, things like patient preferences, and then sub-select amongst those treatment options. And together they can do a much better job. Another area that I'm looking at is industrial control, and there we often have human operators that make really important decisions. So I'm looking at water treatment, using RL for water treatment. So in this scenario, I'm imagining the operator says, we have information about these new pumps. They're really going to reduce our costs. And that choice was a very important choice, actually, making sure that that system runs well. And now the AI can make the system work even better by now re-optimizing automatically that system with the new pumps. So this is the world I imagine going forward. And in order to get these kinds of supportive AI, we really need two things. We need the AI to be adaptive. So, there's nothing worse than having a partner that doesn't adapt to your behavior. That AI has to adapt to how that human operator is working. And the other thing that I think is very important is that the AI has to complement our skills. So the examples I gave you, if you noticed, is that the human was making important higher level decisions. And the AI can make much more of those lower level decisions, something where we have high dimensional information, things that are harder for us to do. And so then together they can be a more effective team. So this talk is called Reinforcement Learning, the next big thing in AI, because I think RL is what's going to help us get both of these things. It enables both of these things. So before I can tell you a bit more about why that is, let me give you just a little bit of background. So I presume this is a relatively general audience. Everyone here knows about AI to some extent, but I'm going to assume that sometimes we have different assumptions about what different things mean. So I'm going to give a bit of background about reinforcement learning and also about machine learning. Okay, so as Cam mentioned, actually, reinforcement learning is this formalism for trial and error interaction. And really, what that means is that it's a machine learning area focused on decision making. So it's a machine learning area because it's data driven, and it is a decision making formalism, which means it cares a lot about autonomous behavior. So first, jumping a little bit into machine learning. When I say it's a machine learning area, one of the things you might think of is supervised learning. So supervised learning or prediction systems are an important part of reinforcement learning, in addition to control. So again, let's do a little bit of background here on supervised learning. And then I'll also contrast that to reinforcement learning. Okay, so supervised learning or in machine learning is all about prediction. So here, for example, maybe you get an image of a cart. Let's say you're a grocery store and you'd like to be able to give customers a prediction of how much the items in their cart might cost. Or maybe you just want to track that information because it would be useful to know. So you might have an image of a cart and you might want to predict what is the price of the items in this cart. This is a standard supervised learning setting, and it's called deep learning for supervised learning if we're going to use neural networks to do so. So here what this might look like is we take that image, we take all the pixels in the image, that gets handed off into our neural network, which is like a little brain, and then it's going to output a prediction for, that's just this scalar that says what's the price of the items in the cart. Okay, so we're actually going to use very similar technology in reinforcement learning. Neural networks are really important technology inside reinforcement learning, and so digging a little bit deeper into this neural network component, one of the nice things about neural networks is that they actually are relatively easy to explain because they do look a lot like what our brain looks like, or at least we like to imagine that they are a little bit of an instantiation of that. So a neural network has a bunch of neurons here as these circles, and each neuron has many other neurons that get inputted into it with connections that are these arrows. Okay, so maybe, for example, this neuron in the center, I don't have a pointer here, but let's say this top neuron in the center has these 4 black neurons coming into it, and depending on their values and the weights on these arrows, the connections, it's either going to cause that neuron to activate or not activate. So depending on different inputs that we get, we're going to get different activations inside our network. Okay, and of course, we don't just want to have this very simple neural network. In general, we'll look at deep neural networks, and now we can imagine that we're going to stack many of these. We're going to have many neurons going into many other neurons, going into many other neurons, and now we're going to get that depth that is going to give us this much larger neural network brain that is going to be able to do very complex things. Okay, so coming back to our example, I'm going to stop drawing these many, many nodes. It's kind of an inconvenient thing to draw, and now we're going to think a little bit about, drawing this in a simpler way. So I'm just going to have each of these layers. There's going to be connections between these layers. And now we can imagine what does an inner layer might actually look like for this supervised learning problem. Okay, so going back to this problem, let's imagine again that we have this input that's a cart. It's going to go through our neural network. And we're going to have many of these neurons. And now we can kind of guess or imagine what one of these hidden layers inside our neural network looks like. So I'm going to label that this R1 to RD. Okay, and one of the things we could imagine is that it extracts really useful properties about this image that then makes it possible to predict something like what is the price of items in a cart. So we really want to take an image, which is just pixel information. It's not a very useful thing to directly predict something about, and go through multiple levels of transformation until there's some useful features that make it easier to make a prediction. So this is very hypothetical, of course. This is not actually what is trained inside this network, but we could imagine that maybe it extracts features that are things like, what are the number of apples in this cart? And what are the size of those apples? And how uncertain am I about the items in this cart? And how many hidden items are there that are occluded by items in the front of this image? And what's the volume in the cart? So these are all the types of things we might imagine that are abstractions or abstract features that the neural network might extract. Okay, and if we get another cart that looks different, we'll have a different image. It's going to produce a different set of features specific to that cart. Okay, so that's the dream of using neural networks, is that it can learn these very complex relationships between something like an image and output something difficult to do, like predicting price of items. And again, that's the data-driven part of this. Machine learning has a lot to offer, and we want to leverage all this technology. Okay, now we can contrast that just a little bit to what actually happens in reinforcement learning. So in addition to wanting to use all that, we also now don't just want to do prediction. I don't just want to give you an item and you predict something about it. We also want the agent to autonomously make choices in an environment. Okay, so that's the reinforcement learning part. So here we might imagine we have this agent. It's, let's say, trying to control, improve control of a water treatment facility for drinking water. And now its actions might be something like changing pump speeds in an effort to save on electricity. So we want to reduce energy costs. Or so its actions might be to increase or decrease certain pump speeds. It might get back a bunch of sensory information from that water treatment facility that says things like, what's the temperature of the water, what's the pH, what's the production of the water, and so on. And it'll also get a reward for, was that a good action or was that a bad action? And now, since this is a formalism for trial and error interaction, the goal is that over time, the agent actually starts taking the right actions to maximize its long-term reward. So it wants to take an action now that immediately gives a good reward, but it also wants to take an action now so that it gets good long-term reward, because its actions now are definitely going to impact what it sees into the future. So this is the central part of reinforcement learning, this interactive behavior component. And of course, a very important part of this, though, is that internal to the agent, it's still going to be making many predictions and using all of that machine learning technology, like I said, neural networks. Okay, so that comes back to why reinforcement learning enables both, is that the data-driven part in the fact that it's interacting with the system through trial and error lets it adapt, and the fact that it can take in this higher dimensional information and find these very complex patterns is how it complements us. So let me give you a specific couple of examples how RL has actually been looked at inside Amii, two very important applications. One is this application from Patrick Pilarski, a fellow in Amii. He's actually going to be talking about this tomorrow, and I think it's one of the most interesting uses of RL. So here the idea is that there's people who have prosthetics, and if they have a prosthetic, it might be controlled by only, say, muscle twitches in the arm, a very not precise signal. But that person needs to use both their elbow or their wrist, and in order to switch between modes, to say, please start controlling the wrist or please start controlling the elbow, they actually have to use their chin to change modes on that prosthetic. Okay, that's a very inconvenient use of that prosthetic. So here the goal was to say, can the RL agent anticipate what mode the person would like to be using their prosthetic in, and then automatically switch to that mode so that there can be a much more smooth interaction. Okay, great. Another example, one that Adam White is actually going to talk about tomorrow, also a fellow in Amii, and this is also a project that I am working on, is looking at how to improve drinking water treatment using RL. Okay, so to me, actually, a lot of industrial control problems are a place where RL is going to be very helpful, and particularly, I think this is a really great use case for RL. So one reason is that it's a sensor-rich system, and there's a lot of different low-level control components of this system. So the human operators right now have a very hard job. They have to do things like decide what chemicals to use, they have to pay attention to filter replacement, they have to do a lot of cleaning themselves, and they also have to make sure the low-level control is working okay. So here, this is a great place for an RL agent to come in and help improve things like, again, like I mentioned, pump speed so that you can reduce electricity use, things like chemical dosing rates so that chemical use can be reduced. So it's both going to make the human operator's job easier, and it's also hopefully going to save them some money by making the system more efficient. Okay, and here hopefully you can see how this is an interactive system. That was the example I gave with how RL would work for this problem setting. That, again, the agent on each time step is going to have to make all these low-level decisions, like what should the current pump speeds be and what should my current chemical dosing rate be. And the reward would look something like energy used over time and if the production of water was good. Okay, so overall, I think RL is going to be really important for getting us towards these applications. And the overall outcome, not just for these two applications, is of course we're going to have smarter systems, and then that means that we're going to have better lives. So there's really three keywords here on this slide. The first keyword is, I think the main thing we're going to get from RL is simply efficiency improvements. We already have a lot of great systems out there. We even have some good automated systems, and we can just make those better. So the water treatment was an example of that. Another one is equity or accessibility. So the water treatment example is another use case for this. There's a lot of water treatment facilities around Alberta in difficult to treat areas. The water is particularly difficult to treat, and it can be hard to get enough people to actually be hired into these positions. So any ability for us to actually improve that and to adjust to different water that's coming into the system could make it much more feasible for these systems to have access to clean drinking water. Okay, and then the last one, of course, is personalized. So adaptive systems are ones that are actually going to adapt to us, and we're going to have much better personalized systems like personalized thermostat control. Okay, so this is the dream, and now you might say, okay, well, based on everything you said, which it seems reasonable that this should already be in our lives and be making our lives better now. But you could ask, is RL already being used to make our lives better? And the short answer, and maybe slightly unfortunate answer, is that that's not really true yet. So there, of course, are some products out there today that use RL, and they're making those systems better. But there is nowhere near the same level of adoption of RL as there is standard prediction systems from machine learning. So that supervised learning setting that I showed you before. Machine learning has changed everything around us. It's in so many of our systems today, and there's nowhere near the same level of adoption for RL. So now I'd like to tell you a little bit about why is that the case, and why we can actually do something about that. Okay, so actually I have 3 reasons for why it hasn't been done yet. So the first reason is, I guess maybe it's the first reason that you might think of as well, is that there's concerns about autonomous systems. Right now, prediction systems are ones where those predictions are maybe given to us and we might do something with those predictions. There isn't an agent just taking actions autonomously. This just seems a little less fraught with difficulty. And otherwise, many of our automated control systems are based on engineering principles. So often using first principles models, they're much more constrained, and there's a good understanding of what happens with those first principles models. And there's just less understanding of learning plus control, and there's less examples of it in the real world. So we just personally aren't as comfortable with it. The second reason is that reinforcement learning, actually, the field of reinforcement learning and research hasn't focused as much on it as they could. And so the reason for this is actually completely reasonable, is that there's really just other lower hanging fruit. So reinforcement learning as a field is relatively old, but it has always been relatively small. So only in recent years has it exploded with the number of people working in it. And there's just lots of things to do first before we move on to the harder problem of getting RL into the real world. So the easiest use case for RL is when you have a simulator, and there's actually lots of useful simulated problems out there. So what that means is if you have a simulator, that means the agent can run perfectly on a computer, and that means there's no safety concerns. You can run with many iterations, many interactions, and given that scenario, then we can actually learn a very good policy. Our algorithms are very good at that. So because there's these examples like games like Go or places with big search spaces like for protein folding, that's a natural place to say, let's see what RL can do there, because we already see it could have a big impact in those areas. But as a result, that means we just have less exploration of how RL would work in a real world where we don't have a simulator and we have much fewer interactions. Okay, and then the third reason is that, at least I think, is just that we haven't really tried it. So I think today we could actually take some of the algorithms that we have developed over the last few years and just start using them. And I think in some cases we'll just see things work and it improves our systems. And of course we're going to see places where it doesn't work and we'll understand those limits, and then we can improve from there as well. So one of my pitches is that the RL isn't being used a lot yet, and one of the ways we can help is to address reason 3 here, which is let's just start trying to use it. So I particularly think that Alberta and Edmonton is a great place to do this. And so let me tell you a little bit now about why I think here is a place where we could lead this RL revolution. So I'm going to give this a name so I can reference it as we go along. I'm going to call it the Alberta Advantage. So why I think we can make RL the next big thing. I think this is actually true for 2 reasons. One reason is that Amii has a world-leading reinforcement learning group. So of course, in order to make RL the next big thing, we need that. And I also think Alberta itself is a very innovative place, and it's particularly a very industrial innovator. And I think RL is going to have the biggest impact in industrial control scenarios, where you're bringing experts like engineers on one side and you're bringing research experts, and together they can solve these very hard problems. So I think together we can actually accelerate each other. Alone we're already relatively strong, and together we're going to be much stronger. So let me tell you first, what Amii can bring. And why it is that I say that Amii is going to be particularly useful for this RL revolution. So I already just said that the time is now for RL to revolutionize our systems, but I actually don't think it's going to be easy. So I mentioned that I think we can take some of our algorithms and just use them, but we're definitely going to run into issues. So it is actually possible, I think, right now to take a problem in a company, use standard machine learning strategies out of the box, and it actually is going to help improve prediction right away. That is not going to be as obvious in reinforcement. There isn't just as standard of tools that we can import. So we're going to need that expertise to understand how we can actually get RL into different applications and where it's going to work well and where it's not going to work well. So it is going to be harder, and we're going to need that expertise. So, and I think Amii particularly has what we need to overcome these roadblocks for 3 properties. So the first 2 are that Amii has a lot of fellows who have always been thought leaders. So they're not interested in following the fashions of the field, but rather saying, what do we need to do next to actually change what we do? And the second reason is that we have a focus on scholarly and scientific work. So that is not to say, of course, that other places do not have a focus on scholarly or scientific work, but I do think we have a very high standard for scientific work here. We really want our work to give us insight into our algorithms, and there's a history of very strong algorithmic and theoretical work. So just to give a little bit of that history, there's so many wonderful fellows in Amii. I can't fit them all, and even in reinforcement learning, I can't fit them all properly onto this slide. But I'm going to give you a few examples of some of the history of really interesting work that's been done. So of course, Richard Sutton is one of the best known people in reinforcement learning. I'm just going to boldly claim that all successes in RL build on his work. And that's a very bold claim, but I think it might actually be true. Chabishep Esfari is the co-inventor of UCT, which is an algorithm that underlies AlphaGo and many other splashy successes since then. And of course, he's done many other really important things in theory of RL. Adam White introduced general value functions, which is a way to encode knowledge. It's a very new way to think about how our agents can encode knowledge, and it's being actively explored across many groups. DeepMind, Mila Berkeley, and of course here as well. Mike Bowling has had a really big impact on the field by introducing the Atari platform, and that's really actually what spurred this big, deep reinforcement revolution. There were some demonstrations on Atari, and from there it has really driven the ambitions of the field. Okay, and of course there are many more. You're going to hear talks from people tomorrow, like Dale Sherman's and so on. And of course, there's actually also many amazing alumni like David Silver, and actually, again, too many to name. There's just really a history of amazing work. Okay, and then the third one, this is the reason I separate out the third reason for why here we are going to make RL the next big thing, is that it's a little different from the first two. It's much more specific. So I think the third thing that is going to be really important for this RL revolution is a focus on continual learning. So having agents that continually learn. So that's a more technical thing. There are many RL researchers in Amii, but actually a lot of us are looking at agents that continually learn. And so now what I'm going to do is tell you a little bit about why I think that type of agent is so important for making progress towards this. And again, then I'll tell you a little bit about more specifically what my lab has been working on. Okay, so continual learning agents. Let me first tell you what an agent is that does not continually learn, so I can contrast to that. So a static agent is one that would use a fixed policy in deployment. Okay, what might that look like? So what we're usually imagining is that we have data logs from past interactions. So maybe previously you had an operator controlling the plant, or maybe you had actually a default controller that was coded up by someone, like if statements or some kind of default controller. So you have logged all the interaction in the system for the last few years, and now you might actually take that data and say, my agent can learn from this. So you might take some RL algorithm, try to take those data logs and extract a useful policy from that. Maybe you just try to imitate the behavior that you see in that log, and then you're just going to deploy that policy as a fixed policy. Okay, an agent that continually learns, in contrast, is one that would actually adapt and learn in deployment. So that means that I'm actually going right back to the picture I showed you before, because that means when it's taking actions in the system, it's getting back observations and sensors, and it's constantly updating this neural network in the background with this new data. And there's no reason you can't also use data logs for that continual learning agent. We can kind of put these two things together, where you can take all that previous data, you can initialize your policy in some way, and then you could continue adapting in the background. So it's saying some of these just a little bit more in words. We're going to contrast these two things. A static agent might be one that tries to imitate the policy that it sees in the data set. And so that means in deployment, on each time step, it sees this vector of current sensory information, let's 100 sensors about what the current status of the system is. And then it's going to try to output an action that mimics what it thinks the policy in the data set would have done, for example. And a continual learning agent, on the other hand, might say initialize this policy, let's say that neural network in its brain, using the data. And then while it's taking actions in deployment, it's actually going to take that new data. There's new data that it gets to see, and it's going to constantly update the neural network. Okay, so based on this description, maybe it seems, obvious that we would want to use continual learning agents. Why not take advantage of that new data? It's much more restrictive to say we're just going to use the static data set, data set offline, and then deploy a fixed policy afterwards. And it's more flexible to allow that policy to keep updating with more information. Okay, but there is a bit of a tendency to want to have static agents because they can seem a little safer. So you can train the agent on that batch of data, and then you can actually try to look at that policy. You can examine it, you can give it test scenarios, and you can see what its behavior might be. And then you might get an understanding of what that policy does before you actually deploy it. And the other thing is, of course, that the interaction between an agent and an environment when it's learning, it's taking actions and updating, that's actually a pretty complex interaction. We can think of this complex dynamical system that could have unexpected behavior. And so it's a little bit disconcerting maybe to not know exactly what this unexpected behavior could be. But I'm going to make the argument that actually, though this might seem true, and so it might still feel worth not using the new data to have that feeling of safety, that is actually not necessarily true. That continual learning agents could in fact be safer, and in fact, we'd want to pursue that direction to get safe agents. So one main obvious reason is that static agents could actually just be unsafe. So if the world imagine you have your water treatment agent and something about the world changes. One of the pumps breaks or the water changes in some way, or just, there's a degradation in a part of the system. We want our agents to adjust when those things happen rather than just continue to do the same thing over and over again. Actually, sometimes you'll find these videos of robots on the internet where there'll be a manufacturing robot, it'll be moving certain things on a table, and then you'll just move the table over a little bit, and it does very disconcertingly weird things when it continues to behave in exactly the same way. So, fixed, unchanging behavior can be very dangerous. So towards that then, in order to have real safety, we actually want to have safe continual learning agents. We want to be able to know that the agent will adjust if something changes. And then we just have to do the hard job of actually figuring out how can we mitigate unexpected behavior? How can we understand what our continual learning agents are going to do? So it's a hard problem, but I think it's one that we can't sidestep. So we're only going to get so far by sidestepping it. We'll take the static agent route, and then we're just going to hit a roadblock. It'll solve some problems, and it won't solve most of the problems we care about. And so again, these static agents are also missing a key advantage of learning in the first place, where we of course want to learn with new data. So like I said, this is definitely the direction we have to go, but I'm also not saying that it's easy. It's not that moving from static agents to continual learning agents is going to be straightforward, but it's something we have to do, and so that's the direction we need to take. Okay, so just summarizing this about why I think continual learning agents are the right bet. So the first point is that learning systems can be more safe. We get biggest gains. The whole point of learning in the first place is to leverage learning as much as we can. So we get bigger gains if we allow the agents to learn from new data online. And the third point is that even though this is a hard problem, we don't yet understand fully what our agents do when they interact with the system. That doesn't mean we have to wait 10 years to figure out how to use continual learning agents. I think there's a feasible route to start doing it right now by just considering slightly more constrained systems. So we can start, we can pursue this more ambitious route of continual agents, but we can start doing those continual agents today in our real systems by just considering what control problems could I run my agent where there's less concerns about about safety concerns. So again, for this water treatment, for example, engineers have a really good understanding of their system. So they might know the agent should never go outside these parameters for pump speeds, and now our agent just gets to optimize within that safe range. So these three things together, I think, mean continual learning agents is the long-term bet, and it's also something we can do right away. So we may as well just start. Okay, good. I'm making reasonable time. So now I'm going to switch to just telling you a little bit about what we're particularly focusing on my lab, a little bit more technically focused, but I'll just give you a brief summary of what I have said so far. So the first thing is reinforced learning is, you can think of it as machine learning for control. That's really what its main goal is. RL really hasn't been used much in applications, but of course we need to start doing that. Amii has been a world leader in RL algorithms, theory, and education, but actually not yet so much in applications. And the key word here is yet. And so I think that's the next thing where we have this Alberta advantage. We can accelerate each other so we can take that expertise in algorithms and theory and education and bring it into the real world. And the last one is that continual learning agents are key to actually get RL into the real world. Okay, so now let me tell you just a little bit more about some of the things that I'm pursuing in my lab, towards this goal. Okay, so actually we have lots of different projects, but I'm going to give you sort of just this very simplistic view of what we think of when we think of an RL system that continually learns, and then I'll just tell you about two of these specific boxes, some of the insights that we have for two of these boxes. Okay, so what I'm imagining here is that the observations come in. So we have a big vector of sensory information. It's going to come in through what I'm going to call the representation module that is going to transform those inputs, produce a new set of features. That's this vector here. And then those features are going to be used directly into the decision-making policy. So that's the thing that's actually going to decide based on this sensory information, what action should I take. But it's also going to feed into a module that makes many predictions about the world. And those predictions are now also going to be used directly by the decision-making policy. Okay, so I'm going to justify these two boxes. So let me tell you about this first box, the representation module, and then I'll tell you about why I think this predictions box also matters. Okay, so what is representation? I mean, we've been talking about features already, and that's really all I mean about what a representation is. So coming right back to this picture that I showed you before, we might imagine that we get some input. It's going to go through multiple layers of transformation. Then it's going to produce some vector or set of features here, R1 to RD. And those should be ones that empower learning. And then from there, the agent will learn just a few more transformations to get whatever its output might be. For us, the output here would be something like what action the agent should take. Okay, so the key here is how to empower learning. But again, because I used this example before with shopping carts, let's just try to use the same thought exercise, but do it now for an RL setting. So let's imagine what these features might look like for water treatment. So again, let's imagine the agent has a bunch of sensor readings. Let's say it gets an input of 100 sensors. That's approximately what we have, actually. And those sensor readings might correspond to things like the turbidity in the water, pH of the water, temperature of the water, and many other things. And now we want this transformation to take many of these sensory readings, which are hard to directly decide what action you should take just from this 100-dimensional sensory information. And it might transform it into features that look like the following ones. So for example, you might get binary indicator features that might say something like the turbidity is high. So when the turbidity gets high, the agent might actually know that it needs to take a certain action, but if it's below some threshold, it doesn't need to worry. And so that's a useful indicator feature to grab. We might have things like even predictive features. So what might the turbidity be in 5 minutes from now? And that might help the agent decide what actions to take right now in order to anticipate that outcome into the future. And you might have features that are, say, combinations of two different inputs. Maybe you want to know the turbidity is low and the water temperature is low, and you want to know that those two things have both happened. So I will make a disclaimer here. These are just examples of the types of features we might imagine emerge. These are like examples of features we could think are useful. That isn't to say that that actually happens. We don't encode these features or force them to occur. We're not actually doing feature engineering. Rather, this neural network is going to learn many of these transformations. There'll be some abstract features internal to the network that should hopefully be useful, like these features might be, but they won't directly correspond to the features I've said here. So like I said, it's a thought exercise to at least reason about what we hope that the network might produce. Okay, so back to what this means for RL, representation learning RL. This is really the focus of deep reinforcement learning, the word deep coming from deep neural networks. And the deep reinforcement learning is just saying, can we bring in all this technology about deep neural networks and bring them into reinforcement learning to make it more effective? So the types of features we care about in reinforcement learning are ones that are going to enable future learning. So the agent's constantly interacting with the environment. It wants to, with its past experience, learn features that are useful when it continues to learn in the future. And it also wants to learn features that are going to keep its policy stable. Now, we've already talked a little bit about what the representation could look like for supervised learning. We're going to exactly port neural networks into reinforcement learning. And so you might just think, all of the strategies there should perfectly help us solve our problems in RL. But of course, as usual, that is not how it works. There's lots of particular problems in RL that make the representation learning question in reinforcement learning different from the supervised learning setting that we really need to tackle. In fact, the two settings are so different that our questions can look very different. So I'll tell you at least 3 things that make these two settings so different. One of them is that our data is temporally correlated. So of course the agent's interacting constantly with an environment. That data is naturally temporally correlated. That's very different from the examples, say, with those pairs of carts and predictions of prices that are just random samplings of carts. Okay, and temporal correlation of inputs intuitively should have a big effect, but it also seems to particularly interface with neural networks in interesting ways. Interesting things emerge. The other thing that's very important is that we have delayed output information. So again, we don't just get to see cart and then price. Our agent takes an action now, and its actions have long-term consequences. So it could take an action and wait for many, many steps to see the outcomes, but that isn't necessarily a good idea. So we have to think about how can we smartly deal with delayed output information. And the last, but also very important thing is that the data is not passively collected. The agent is taking actions, it's impacting the reward it gets, and it's also impacting the data it sees. So it has to reason a little bit about how does the way that it's behaving actually cause the neural network to possibly suffer in terms of learning or learn better. Okay, so these 3 things are very different from the supervised learning setting, and like I said, make us have to ask different questions. So one of the questions we have been looking at a lot is what representation learning approaches are particularly effective for reinforcement learning. Okay, so we've looked at many different things. I'm going to tell you about one interesting insight that we have, is that sparsity helps. Okay, what does sparsity mean? So the one particular form of sparsity we have looked at is sparse activation. Okay, so what sparse activation means is, if again, I had this big neural network, I had many different nodes. I mentioned that neurons feed into other neurons and they cause them to activate or not activate. So it could be 0 or it could actually be some number greater than 0. If we have sparse activation, it just means that for a given input, only a small number of the nodes are actually non-zero, that are actually active. So what that means is now our representation, this learned thing in the middle, what we imagine is that instead it's going to look something like this. We're going to have a much, much bigger representation, but only some small parts of it are going to be used for any one given input. So if I see one input, maybe feature 2, 7, and 10 are active, and the rest are all 0. And then if I see a different input, maybe feature 1 and 100 are active, and all the rest are 0. Okay, so we've looked a lot at how do we actually learn such sparse activations in a neural network? It doesn't just emerge naturally, so we have to force it to learn those kinds of sparse activations, and we have found that it actually really helps improve training, particularly when you're learning online or learning continually. The next thing that we're also looking at is, so we've looked a little bit at sparse activations. We have definitely found repeatedly that there's some benefit to incorporating sparse activations in RL. We're also looking a little bit more also at sparse connections, so sparsity in general throughout the network. And actually this is sort of inspired by our brain. Our brain is not fully connected. It's not every neuron is not connected to every other neuron. And is also a sparse activation in it as well. So there's some inspiration there, but then there's also some technical reasons why both can be good. So if I were just to tell you what sparse connections look like, again, going back to this picture of a very deep neural network, here when the ... implies that all the nodes in that first layer are connected to all the nodes in the second layer. It's kind of hard to draw that many arrows. So those arrows, you can imagine those arrows are all repeated, everything's connected to everything. Sparse connections would just mean that each node here, for example, might just be connected to 1 or 2 or 3 other neurons that they're going into on the next layer. So this first neuron is just connected to the second neuron in the next layer, and so on. So many, many fewer connections. Okay, this in general I think is a really important direction because we really want to have bigger networks. We want to learn many, many different possible features. That actually does seem to be a general trend that's worthwhile, but it quickly becomes way too expensive if everything is fully connected and everything is fully active. So I'll just give you a very basic example because sometimes it's hard for us to imagine how big numbers can get when we start making things slightly larger. So let's imagine I just have 1,000 neurons and 1,000 neurons for 2 layers that are all perfectly connected to each other. Automatically, I'm now going to have 1 million weights that I have to learn. I have 1 million connections that I have to figure out how important is this neuron for this other neuron. That is a lot, and that's only 1,000 and 1,000. That is a very small network. Okay, if I have, say, sparse connections, I can have much more efficient computation. It's just going to scale linearly with the number of input neurons. So if I have 3 connections per neuron, then now the number of weights is only 3,000. Okay, and sparse activation further reduces cost because whenever we query the network, we're effectively querying a subnetwork. If we input and there's a bunch of zeros, it's like we've removed those neurons and we're only considering a small subset. So each layer is only ever considering a small subset, and so it gets us a lot of efficiency. So many less things to learn and also much more efficient to query, but we still get the advantage of having many, many possible features that we could be considering. So I think this is a really important direction for RL. Okay, let me tell you about the other subcomponent here. Okay, so that was, representation learning is very important. Sparsity is one thing that we have been looking at amongst other things. And another thing we've been pursuing wholeheartedly is looking at having the agent learn predictions about its world and then incorporating those into its decision-making policy. Okay. So again, maybe that high level is not too controversial, but let me tell you why this is an interesting and not that common thing to do. Okay, so the goal here is to have a parallel learning system where we want the agent to learn about many things in parallel. And so here mainly it wants to learn about many predictions and policies in parallel. So what does that actually look like? The agent is executing its current behavior, its current strategy, again, let's say for a water treatment, so that it does the best job it can treating water. But in parallel, it wants to counterfactually reason about other things that it could be doing. So it sort of has to reason about many different possible things it could be doing, but only learn on this single stream that's under its current behavior. Okay, so many current systems mainly focus on, I have a single stream, I just want to improve which actions I take, and they aren't necessarily trying to make these many other predictions. So what could these other predictions look like? So particularly the agent is going to reason about other behaviors that it could do. So for example, I have my little water treatment agent here. Maybe it's asking how much energy do I save if I turn off this pump for 5 minutes? Or it might ask a question like, what happens to turbidity if I increase my pump speeds? So, those are asking questions about other things it could be doing. And of course, knowing the answers to those questions could help improve what decisions it takes on this time step. Nonetheless, these are about other behaviors rather than the one that it's currently following. So like I said, it's kind of natural. I mean, that's of course what we do. We are, doing one thing in the world. I'm taking actions right now, but I might be asking many different things internally. I might be reasoning about the outcomes of many different things. But for a long time, this hasn't been that easy in RL for technical reasons. That's really ironic. So what has happened recently actually is even just in the last 5 years, we've had really important algorithmic advances in terms of stably learning many of these types of predictions at the same time, so in parallel. It was always feasible to learn them in sequence, and actually that was pursued sometimes, that the agent would learn about one type of behavior, then it would learn about another type of behavior. You can see that that strategy doesn't scale very well. So we want the agent to reason about many things in parallel, and now we have the algorithms that let us do this effectively. And so now, because we have the algorithms that let us do it, we can start really exploring these kinds of parallel learning systems and seeing what they can do to improve our decision-making policy. So that's something that we're actively doing, is now asking, now that we can do it, how should we use it? Like, how can it actually help our system? Just concluding a little bit, bringing these two pieces together. I mentioned why I think learning many things in parallel is good. Sometimes whenever you start incorporating components into your system, positive side benefits occur. Sometimes the world is kind. So learning many things actually has some auxiliary benefits. And this is for mitigating catastrophic interference. So I mentioned this kind of ties back to representation learning. That's why I'm telling you about it. Neural networks have this problem that's called forgetting, or they can sometimes suffer from what's called forgetting under temporally correlated data. So the type of data that our RL agents will see. So what that means is that the network might have previously learned, I'm going to use this very simple example. The agent might have learned Spanish before, and now by learning Spanish, it actually overwrites the fact that it knew French. That would be a ridiculous thing for our networks to do. We wanted to learn French, then we wanted to learn Spanish, and it should be able to keep both of those languages. What we find sometimes in practice is that our neural network will learn something in one part of the space, then it will learn something in another part of the space, and that new learning causes unlearning in the original part of the space. And that's not the kind of behavior we want. So we're always asking, how can we make sure that our neural network can incorporate new information without forgetting too much of the things it has learned in the past? So actually these two things together can help us do this even better. Sparsity seems to help in this way, as so does learning many predictions in parallel. So the intuition here is that sparse connections and sparse activations, each time the agent updates those weights, it's always only going to update a much smaller part of the network. So it's less likely to make big wholesale changes to the whole network, and the network is going to stay more stable over time. And for learning many predictions, instead of just learning something about action outputs and that again changing this giant network, if you're learning many, many predictions, well then it's reinforcing previous learning. So it's constraining the network to make sure that it remembers many things that it needs to know. So these two things together have this nice benefit. Okay, that brings me to my final point. So like I said, we've been looking at sparsity, we've been looking at learning many things, and actually one of the things that we have been doing as we're looking at this full RL system is we're starting to get closer now to asking, how can we integrate all these pieces that we have and to understand what the full RL system looks like? So for many years, we just looked at how do we get sparsity and what are the algorithms for sparsity? Or we looked at how do we get good algorithms that give us this ability to learn many predictions in parallel. And now we're finally moving to how can we put all those pieces together? So I do think we have a lot of the pieces. We've made really big algorithmic strides to put together these effective systems. But now our next step is really understanding what the behavior of those systems are. So as we started putting together these pieces, we've noticed, again, naturally, that when you put together several components, the interactions between them can cause unexpected behavior, and there's a lot to understand there. So, I believe there's a new frontier in actually becoming experts in the science of understanding our RL systems. So what I mean here, for example, is that interactions between our components can be complex in a way that is bad, because since small choices, maybe this algorithm on its own is great, this algorithm on its own is great, and when I put them together into my larger system, they don't cooperate well, and the system just is not very effective. On the other hand, we can also find that interactions are amplifying. So in the example that I just gave about sparsity and learning many things in parallel, those are just two parts of our system that we wanted to do, and together they actually also solved a third problem. It helped us deal with this forgetting issue. So the sum of the parts was actually greater than each of those parts. It created a system that was even more effective than just those two effective subcomponents. So I think there's a lot here to understand about our RL systems, and my group is starting to look a lot more at how do we take a larger complex system and then understand why it is failing and why it isn't failing. And I encourage others who are in research to start looking more at these as well. Okay, so the key takeaways, this is my very last slide, just popping all the way back up from that much deeper technical dive. That we have the Alberta advantage, so we have the opportunity to lead in developing and using RL in the real world. I think towards this, agents that continually learn are key if we're actually going to do this. And even though this is a hard problem, I think now is the time to start, and we have the tools to make real progress on it. So thank you very much.